All right, so now let's talk about some real life examples where we have exponential growth and exponential decay. One of the most common examples of exponential growth is in investments earning compound interest. There are two different formulas for compound interest. Formula number one is for n number of compoundings per year. Compoundings means how many times you actually earn interest. All right. So N refers to the number of times per year that your interest is compounded. How many times do you earn interest in that year? We have A is equal to P times 1 plus R over N, all raised to the N times T. In this formula, A represents the balance in the account. The amount of money that you have is equal to P, the principal. That is the initial investment that you make, times the quantity 1 plus R. R represents the annual interest rate. And this is important. The interest rate must be plugged in decimal form. All right, so whatever the interest rate is as a percentage, take that and divide it by 100. Okay, we need the decimal form of the interest rate. And and T is the time measured in years. All right, T is the time measured in years. And as we said, N is the number of times you are earning interest. How many times per year are we earning interest? The number of compoundings per year. Now, we also have a formula for interest that is compounded continuously. In other words, you are continuously going to be earning interest on your investment. The formula that we want to use for compounded continuously is A equals P times E raised to the RT. P is still your principal, the initial investment. A is still the balance in the account, the amount of money that you have. E, this is our natural number E, which we talked about earlier in the chapter. And R is our interest rate. Again, make sure you plug in R in decimal form. And T is the time measured in years. So let's see if we can't put a example together here. A total of $12,000 is invested at an annual interest rate of 9%. Find the balance in the account after 5 years if it is compounded quarterly, monthly, and continuously. So we have three different scenarios that we are going to have to go through. Let's start off with compounded quarterly. All right, quarterly means that we have 4 compoundings per year. So we want to use the formula A equals P times 1 plus R over N to the NT. All right, here's a piece of advice. Anytime you are doing a problem that involves a particular formula, start by writing that formula down. Then we can begin to plug in. P, our principal, is going to be 12,000. That's our initial investment. Times the quantity 1 plus R. The interest rate is 9%. As a decimal, that's 0.09 divided by, if we are compounding quarterly, there are 4 quarters to a year. Therefore, N is going to be 4, all raised to the 4 times T. And notice I have used function notation here. This is the amount of money that I have as a function of time, T in years. A of T is equal to 12,000 times the quantity 1 plus 0.09 over 4, all raised to the 4 times T. Well, what do we need to plug in for T now? We're looking to find the balance in the account after 5 years, so let's plug in 5 for T. Plugging in 5 for T, and obviously using our calculator in this case, gives us approximately $18,726.11. Make sure you are comfortable plugging all of this into your calculator. The most common mistake that I see is that students raise this to the power of 4 and then multiply by 5. And your calculator doesn't know that you really want to raise this to the entire quantity of 4 times 5, or 20. So when you plug this into your calculator, two options: raise this to the 20 power or raise it to a parentheses 4 times 5. In other words, put parentheses around the entire exponent. If you're having trouble plugging in your calculator, make sure you come and see me. All right, now let's try the next scenario, compounded monthly. All right, we're going to be using the exact same formula, compounded monthly. Well, they're 12 months in a year. That means we are going to be earning interest 12 times in that year, once every month. So A of t, A as a function of time, is equal to 12,000 times 1 plus 0.09 divided by 12 raised to the 12 times t. Again, same formula. The only thing that's changing here is the number of times per year that we are earning interest, our number of compoundings. All right, again, we want to find the balance after 5 years. So let's plug in 5 for t. Evaluate A of 5. We have 12,000 times the quantity 1 plus 0.09 divided by 12 raised to the 12 times 5. And again, as you plug that into your calculator, either raise it to the 60th or put parentheses around the entire exponent. All right, parentheses 12 times 5. That gives us approximately $18,788.17. And finally, let's analyze our investment if our interest is compounded continuously. For compounded continuously, the formula that we want to use is A equals P e to the RT, A PERT. Well, A of t is equal to 12,000. Again, that's our principal, our initial investment, times e raised to the 0.09. That's our interest rate in decimal form, times t. And again, we want to evaluate this at 5 years. Let's plug in 5 for t. This is 12,000 times e raised to the, remember, parentheses around the entire exponent when you plug it into your calculator, 0.09 times 5. And that gives us approximately $18,819.75. So, out of these three options, which one's the best one? Well, compounded continuously. Obviously, it's going to give us the most money. All right, so there is a common example of exponential growth with our investments. Now, let's talk about a common example of exponential decay. One of the most common examples of exponential decay is observed in radioactive decay. Some of you guys may have learned about this in your chemistry classes. This is the process by which an unstable atomic nucleus spontaneously breaks down and loses energy in the form of radiation. Now, I am not a chemist or a nuclear physicist, so don't ask me any more information about that, right? But what happens is our atomic nucleus is breaking down. It's becoming smaller over time. All right, so as a result, radioactive elements have what is referred to as a half-life. This is the period of time that it takes for the amount of a radioactive element to be cut in half. So for example, if I have radioactive plutonium, 239Pu, that has a half-life of 24,100 years, and at time 0, I have 8 grams, that means after 24,100 years, I am going to have 4 grams. The amount that I have gets cut in half. And if I go another 24,100 years to t equals 48,200, then my amount is again going to be cut in half. What's half of 4? 2. And if I go another 24,100 years, that would bring me to t is equal to 72,300, then I would have 1 gram left over. Again, the amount that I had previously gets cut in half. And if I went another 24,100 years to t equals 96,400, I would have 1/2 of a gram. So on and so forth. So if we were to plot this on a graph, here's what the shape of our function would look like. And notice this can be modeled by exponential decay, right? Here we have q of t is equal to 8 times 1/2 raised to the t divided by 24,100 would be the particular equation in this part. Now, I'm not going to ask you to come up with equations just yet, but you should be able to use an equation to find out some information. So, for example, here we have the half-life of radioactive radium, that's 226 Ra, is about 1599 years, 1599 years. The quantity present after t years is modeled by the function q of t is equal to 25 times 1/2 raised to the t divided by 1599. Determine the initial quantity. All right. One thing to make note of is that whenever you're asked to find an initial condition, an initial quantity, we are referring to the start of time. And time starts at 0. That means we are going to evaluate Q of 0. Plug in 0 for t. Q of 0 is equal to 25 times 1/2 raised to the 0 divided by 1599. Well, 0 divided by 1599, that's still 0. And 1/2 raised to the 0, well, any non-zero number raised to the 0 power is 1. So this becomes 25 times 1, which gives us 25 grams for our initial quantity. How much is present after 2,500 years? Well, to do that, all we have to do is evaluate Q of 2,500. Plug in 2,500 for T. Q of 2,500 is equal to 25 times 1/2 raised to the 2,500 divided by 1599. All right, and so all we have to do is plug this into our calculator. Now, again, one thing you have to be careful of is you need to put parentheses around this entire exponent. All right, parentheses around your exponent when you go to plug it into your calculator. And this gives us approximately 8.46 grams. All right, and if you were to graph out our function, our Q of t function, this is what it would look like. Notice at time t equals 0, we have 25 grams. That's our initial amount. And as time goes on, our amount decreases exponentially. We have exponential decay. All right, that's the end of chapter 3.1, exponential functions.